All right. Hi, folks. Welcome back to Physics with Captain Rod. Making this video here to help you out with your finishing your ballistic pendulum lab. All right, so we should have taken measurements here. We should have the mass of the ball as a number that you've got, right? And then, the mass of the pendulum. Hopefully you've measured that. And then hopefully you have an angle here, an average angle, right? So you should have numbers for all of these quantities. And let's talk about number 4, where it says to use the swing angle to find the speed of the ball pendulum just after impact. So I inserted some photos here. This is what the system looks like before the ball enters the pendulum. So you got to imagine the ball like at this position, and it has a velocity in this direction that we're going to call, like, whoops, put this somewhere, velocity ball picture 1. And to analyze the impact, we're going to need to know the velocity of the pendulum just after impact. All right. So I'm going to go down for another picture here. So imagine, all right, here's, whoops, come on, draw. Sometimes this gives me a little trouble. So here's our ball. A picture. This is the instant it comes out of the firing apparatus. Its velocity is this way, right? Velocity ball picture 1, and the pendulum at that location. The pendulum is still sitting here, and the velocity of the pendulum is 0. After the ball hits the pendulum, and I'm going to draw this off to the side here, right here. Ball is in the pendulum. The entire thing is moving to the right now at some speed here. Let's call this velocity of the pendulum in the second picture. So this is picture 1 just before impact. Here's picture 2 an instant after impact. And then the highest point here, I'm going to call picture 3. So equation-wise, if we equate the momentum of the ball in picture 1 to the momentum of the system in picture 2, that's going to allow you to write out, all right, m mass of the ball, velocity ball picture 1 equals, I'm going to put a large M here for the mass of the entire system, ball and pendulum, times the oops, turned off on me again, times the velocity of the pendulum in picture 2. Right now we're going to go after this. So as the pendulum swings up to this position, that is a potential energy to kinetic energy thing. All right. So if we put a datum basically right through the pendulum, darn it, quit drawing on me again. If we put a datum right through the pendulum, you'll notice that we have a height difference here, and I'll talk about how to find that here in just a minute. And if we do the work energy theorem between 2 and 3, and I'm running out of room, so I'm going to do this very shorthand. We have the kinetic energy, 1/2 m velocity pendulum picture 2 squared equals the potential energy in picture 3, mgh. All right, now let's talk a little bit about, all right, how do we find h? I'll go back to this picture for a moment. One of the things I probably should have had you measure and didn't is this distance to about here. I measured that for you just now in the lab. That distance is 29 centimeters. You can go ahead and use that for your lab. And then if your lab doesn't work out, you can blame me. And then when the pendulum swung up to some angle, that distance is now looking like this. This height difference right here that we call h, right, that's going to equal 29 centimeters minus 29 centimeters times the cosine of this angle. And I'll describe, why that is. Because do this in orange, this distance right here. Right, if you look at this triangle, the hypotenuse of that triangle is the 29 centimeters. So the orange distance is adjacent to that. That's equal to 29 centimeters times the cosine of, I don't know why that quits writing on me, times the cosine of whatever angle you measured, right? So this is how you find the height difference for the potential energy term if you put a datum here. So kind of going through this. So we have a work energy theorem between pictures 2 and 3, and I just discussed how to get the height difference. So out of this you can get the velocity of the pendulum in picture 2. Then that can go here to get velocity of the ball in picture 1. So that's this vector right there, the velocity at which the ball is coming out of the pendulum at. All right, so now to finish the problem, I think what I'll do here is probably go to another page. Give me a moment. Okay, here we go. So now we got to do the motion problem. So this is going to be fired off of a table. Right now, the pendulum is no longer important. What's important is the ball. So the ball is going to be fired perfectly horizontally at a velocity ball picture 1. This is now a numerical value that we know. And it's going to hit down here somewhere. Now, one of the things I asked you to measure was this height, and hopefully we measured this correctly. You wanted from the bottom of the ball to the ground, because that is the height that the ball is going to fall by the time there's contact. In a little review now, this is a two-dimensional problem. So let's talk about the x direction and the y direction. So our velocity in the x direction is constant, not changing. And that means a quick sketch of it, velocity against time, or I'm sorry, position against time is linear. It's going to look like this. And the equation for this line, there's x equals velocity times t. This velocity is this one, which is this guy, right? In the y direction, and I'm going to do two graphs in the y direction, our velocity graph in the y direction, right, at t equals 0, the velocity is 0. And then remember, like 1 second later, the velocity is going to be negative 9.8 and then negative 19.6 and so forth. So this is going to look like this. And the equation for this line is going to be v equals negative 9.8t, leaving out the units. And like always, this area here gives the distance traveled. So basically this is going to come out to y equals minus 4.9t squared. Okay, so take your known height, that's going to go here, get your time out of it, that will go here, and there is your distance. And that should get you ready enough, that should get you to a position where you know where to put your can next Thursday morning. So hopefully you get your lab done, no problem. You should get a value, I'll just give you a ballpark figure, you know, should be probably, you know, more than a meter but less than 3 meters. You should get something kind of in that region. All right, if you get 4.5 meters or something like that, there's a problem. Or if you get 0.6 meters, there's also a problem. But somewhere in the 1 to 3 region. And again, hope you have a great weekend, and we'll see you next week.